Hello friends, I hope it is clear to you, the sharpness and everything. So if I tap on it, I think it will focus properly. Yeah, okay. So hello everyone and welcome to another session on semiconductors. Today we are going to discuss very important things. So let's start with the concept of recombination during the forward current. See, when the current is flowing in the PN junction in the forward bias condition, always there are recombinations happening between the holes and electrons. It means that the electron will jump from the conduction band into the valence band, into that hole, and during that process both the electrons and holes may get destroyed. So let's take an example here of this is a entire PN junction which I have divided into this P side here and N side here, and we can see that there is a this PN junction is a forward bias with the battery here, and so the current is flowing. So obviously the current will be leaving the positive terminal of the battery and going like this. So obviously we know that if the current is going, let's say in this clockwise fashion, then electrons will be moving in opposite direction, isn't it? Okay. Now let's say there are electrons here in this valence band here, which is shown, and these top electrons, they indicate the electrons in the conduction band. So N side has got lots and lots of free electrons on the conduction side, whereas P side has got lots and lots of holes here. Okay, now we know that the battery, which is having a positive terminal here and negative terminal here, it will create some kind of electric field like this here. Obviously the electric field of the battery drives the current. So because of the influence of this electric field here towards right, the electrons in the valence band of the P side, they will be drifting like this. So they will be drifting like this here. So we know that electrons need to move like this for the current to flow. So let's say we start from here. We know that the circuit needs to be completed. That means a charge needs to go right here and then it needs to come back. So this electron in the valence band is going from one hole to another, one hole to another, one hole to another, like this, and then it comes out. See, instead of saying that electrons are going in the valence band towards the left from one hole to another, we can say that the hole will be going like this, isn't it? So generally actually we assume like that the current is because of this positively charged holes. So these all things you know very well by now. So let's say we start with the valence band electron, and valence band electron goes like this, comes out here, and it is dumped here, and this electron here now is shifted to the conduction band. So this electron here, or maybe some other electron, so this electron has come here, this electron which was going here, it has come here, and let's say because of the again the electric field of the battery here, this electron is going here like this, and let's say this electron, it falls into this hole. So what we have done here, we have completed the circuit. How? We started with this. We said that this electron is moving like this from one hole to another, which means that the holes are moving like this. So this is like the direction of movement of holes. So electron moving like this in the valence band, going here, coming here, and even if we assume that this has stopped here, some other electron, because of the electric field of the battery, some other electron will be going like this, and then it may fall into the hole here, because there are lots and lots of holes, isn't it? So since in P side has got lots and lots of holes, so electrons, when they diffuse from N side to P side, definitely there is a probability that they may go into those holes. Now when they go into the hole, we started from here, an electron has again reached here. It means that the circuit is complete, and this circuit has completed, and a part of the circuit completion is this recombination. So that's why we can say that this half part, the electrons go in the valence band, and so the conduction is done by holes, and this half part, the electrons are moving in the conduction band. Electrons are moving in the conduction band, and so the current is carried by the electrons. So from here to here maybe majorly by electrons, and maybe from here to here majorly by holes, and then obviously within the conductor the electrons are the one which carry the current. So during this recombination, what happens? Actually the electron goes from the conduction band to the valence band. If you remember this, this is the EC level and this is the EV level, and whenever an electron goes from the conduction band to the valence band, it loses energy. Now this energy is lost in the form of photons. And so what happens is that whenever an electron goes from conduction band to the valence band, photon is released, and maybe we will be able to utilize that photon, isn't it? For example, this conduction band of silicon and valence band of silicon are shown here, and we know that the energy gap is 1.1 electron volt for silicon. So whenever the electron will be coming back to the valence band during this recombination, it will be emitting a photon, but we can't see that because we can see only from red to violet. A red, which is having a 700 nanometer, has approximately 1.77 electron volt of energy, whereas the violet one has 3.105. So we can actually generate light, because when we flow current through the PN junction, lots of recombination will happen. Thousands and thousands of recombinations will happen per unit time, and so thousands and thousands of photons will be emitted. But there is a problem here, that the thousands and thousands of photons which are being emitted in this silicon, those photons will have an energy of around 1.1 electron volt only. So this 1.1 photon energy doesn't come in this range of 1.77 electron volt, which is the one for the red, to 3.105, which is for the violet. And so this 1.1 will come beyond this red. It means in the infrared region, isn't it? So although we are getting lots and lots of light because of the recombination, we will not be able to see it. So what do we require if we want to see that light? We want to make this gap a bit larger. So instead of using silicon, there are some other materials. So some other materials are like gallium arsenide phosphide. So this kind of semiconductor materials, they have their band gap of the order of, for example, 1.9 electron volt. So this 1.9 electron volt, you see here, it falls exactly between this 1.77 and 1. So it falls in the visible spectrum. And so when the electron will be recombining in the semiconductor made by this, then we will see the light coming out. So red light. So semiconductors find their application in making light emitting diodes. You know what the light emitting diode is? It means that whenever the diode is forward biased and current is flowing through it, it will emit light, and we will be able to use that light. So let's check some advantages. Okay, one of the advantages is that it is fast on-off switching capability. What does it mean? See, you might have seen some disco lights, isn't it? So immediately there is a red, and then there is a green one, and then there is a blue, and then it keeps shifting, and some kind of a pattern is formed, isn't it? Design, decoration kind of thing is done. Now this can't be done using incandescent lamps, because if you remember those incandescent lamps, if we switch on the bulb, it takes around 2 to 3 seconds to glow, isn't it? Why? Because the filament gets heated up slowly from red to orange to yellow and so on. Similarly, when we turn it off, what will happen? Again, it will take some time to cool down, and so slowly its intensity will decrease. But in case of disco lights or something, we want the this light to change its all these things we want to happen very fast. So in case of this LEDs, which are made by this PN junctions, as soon as we open the switch, immediately the current will stop. And as soon as the current stops, recombination stops. And as soon as the recombination stops, what will happen is no current. So one of the advantages is that these LEDs can be made to use discos, and we can have a nice dancing and everything, isn't it? Okay, low operational voltage, because we know that the PN junction here, it is sufficiently forward biased even with a potential difference of as less than 0.7 volt, isn't it? We remember the PN junction characteristics. Okay. So low operational voltage, low power, because see, in case of incandescent lamps, lot of energy is going into heating the filament, and only a tiny fraction of it is converted into light. So less operating voltage, so that's one advantage, and then less power also consumed. No warm up time required, as I already explained. Then light is emitted is nearly monochromatic. Okay, because of the constant band gap, isn't it? So one semiconductor will have only a one band gap, and so the energy of the photon released will be of one single value. Whereas when the filament gets heated up, the black body radiation, they will be emitting light of so many wavelengths. In fact, if you remember this, what is that called? Now, Planck's theory. You may remember this E lambda versus lambda, and then there will be this lambda max here, isn't it? So lots and lots of photons of different wavelengths with different energies are emitted in case of black body radiation, which happens in incandescent lamps. But here we can get exactly a monochromatic light. Why do we require a monochromatic light? Maybe we want to do some kind of experiment, maybe Young's double slit experiment. So for that we can't use different wavelengths, isn't it? Otherwise no fringe pattern will be formed. So there are many uses of monochromatic light. So, and then long life. I don't know how that is, but yeah, long life than incandescent lamp. Okay, so LEDs are made up of semiconductors that are heavily doped. Now why we want this to be heavily doped? Because lots and lots of high doping will also mean lots and lots of holes and electrons, isn't it? Lots of holes on the p side, lots of electrons on the n side, so more number of recombinations will happen, huge amount of current will flow. And so these LEDs are made up of semiconductors which are like heavily doped here. Moving on now.